So as we get started with this topic called related rates, first of all I want to paint a picture for you. Okay? And that picture is of me blowing up a balloon. I've got a deflated balloon. By the way, for the purpose of this mathematical demonstration, let's assume that as I blow up the balloon, it is perfectly spherical. You okay with that? Yes. All right. So I take my first deep breath, and I blow into the balloon, and the balloon goes. I take my second breath. Does it double in diameter with my second breath? It tends to get only a little bit bigger. And with my third breath, a little bit bigger. There's a big change in the diameter with my first breath, and the changes afterwards seem to be smaller until, of course, I blow so much air into the balloon that it explodes. Edmund.
Oh, no, I was just chasing something.
Okay. So what I want you to see is that the amount of volume in the balloon changes, the radius or the diameter changes, but it's not a linear relationship. They change, they're related to each other, but it's not a straight linear relationship. Now, in calculus, we've been looking a lot at rates of change. Sometimes we call those rates of change slope. Sometimes we call them marginal revenue or marginal costs, as in some of the problems from 4.4. But the idea is that we can look at how things change using the idea of derivative, and we're going to look at that today in a series of problems having to do with related rates. Let's start with the balloon example. Does anyone know the formula for the volume of a sphere? Edmund. 4/3 pi r cubed is correct. It's got a cube in it because it's a volume. It's got a pi in it because it's circular. And the 4/3, we'll find that out later. That's the volume of a sphere. Now, I'm going to start pumping up the balloon, the sphere. Okay? I'm going to change its volume. What kind of units might I use to describe on how quickly I'm pumping up the spherical balloon? What kind of units might be appropriate? Ryan, do you have a suggestion? Inches cubed per second? Because inches cubed is a measurement of volume per second because it's a rate of change. Inches cubed per second. A change in volume per a change in time. I said that in English. Let me say it in mathematics. A change in volume per a change in time. A change in volume per change in time. dV is a little bit of volume change. dt is a little bit of time change. A change in volume per change in time. Now the question could come up, well, how do I start here and end up there? What tools do we have to make this kind of notation stuff? Parameterization. Because that's how we usually get t's into things. That's a reasonable thing to say. I'm going to do something that's going to seem totally unreasonable, though. Are you ready? You want to know how we get there? We take a derivative. Way. I know that's a big surprise, this being calculus class. I'm going to take the derivative of volume. Of course, the derivative, if I take a derivative of one side, I've got to take a derivative of the other as well. What seems totally unreasonable and totally surprising every time I teach this is what variable I'm going to take the derivative with respect to. And the answer is I'm going to take it with respect to time, even though there's no t variable anywhere around. It seems totally unreasonable, but that's what we do. I take the derivative of volume with respect to time. And I do, whatever I do to one side, I have to do the other. And pretending that the right-hand side of the equation doesn't exist, wouldn't that derivative, the derivative of v with respect to time, wouldn't that create a dv dt?
Yeah.
Sure. And now all I have to do is say, what's going on over here? What happens when I take the derivative of this side with respect to time? Well, I bring up my last analogy for this first example, and that is, I'm pumping up the balloon, and the longer I pump it up, I'm using a bike pump. This is the international symbol for bike pump. I'm pumping it up, and for the longer time that I pump it up, my arm's getting tired. I'm waiting for you guys to. The balloon gets bigger. So volume changes with time. Wait, volume changes with time. If I told you that I was pumping up the balloon at a rate of 10 cubic inches per second, and I told you I pumped it up for 10 seconds, could you tell me the new volume? Started at 0. I pumped it up for 10 seconds, 10 cubic inches per second. 100? Right. Oh, wait. That means if I tell you the time, you could tell me the volume? If I tell you the time, you could tell me the volume. That's an example of a what? Starts with an F? Function. So V is acting like a function of t. Wait, I start pumping it up, and not only does the volume change, but so does the radius. The radius is going to act like function of time as well. For the longer I pump it up, the radius continues. And although it may require more work, maybe a calculator, if I tell you how long I'm pumping it up, you could be able to convert it to how big the radius is. So radius is also a function of time. Let's just say it's implied that radius is a function of time. So what happens is that when I take the derivative of this side, I'm going to look at that r not as a variable, but rather as a function. 4/3 pi. The outside function here is 3. Keep the inside the same. Reduce the power. And don't forget about the chain rule. R acts like a function of t. V acts like a function of t. Whenever I take the derivatives with respect to t, I end up getting a chain rule, the RDT or the ddt. Clean up. 4 pi r squared dr dt. That is a relationship. That is a relationship between the change in volume and the change in radius. Should we go back to Ryan's suggestion? He suggested that we could fill up this balloon at a rate of 10 cubic inches per second. Is that big or small? Is that faster? 10. What's 10 cubic? 10 cubic inches? Cube root of 10 is a little over 2. A little over 2, so that's a square that's 2 by 2 by 2, or a little bit bigger than that. That's a pretty slow rate if I'm blowing it up. interested in this question. If the rate that we're filling up the balloon is 10 cubic inches per second, what is dr dt when r is 1? This is not fun. You're gonna do this to me, is it?
You have both in your hand.
It doesn't matter. It says the eraser's gone. It should act like the eraser's gone. All right. I'm gonna have to go over here because I can't erase. All right. Well, let's plug in what we know. Here's what we know. We know that dv dt is equal to 4 pi r squared dr dt. Do we know what dv dt is? 10. 4 pi is 4 pi. Do we know what r is? I'm interested in what is dr dt when r is 1. So I'm going to put 1 there, square it, dr dt. I think I can solve that. I think I can solve that for dr dt. I think it looks something like dr dt is equal to 10 divided by 4 pi. And I would love to have a decimal approximation of that.
You okay?
7 point, one more time? 854. Units, please. Nope, not inches cubed. This is a measurement of how radius is changing. How do we measure radii? In inches, not inches squared or inches cubed. Okay, inches, but it's a rate of change in the radius per time. Per second. All right, isn't that great?
What is it, 7 point what?
7 point, or let's just call it 7.8 inches per second. If I'm pushing the, if I,
Why would it be so big?
it can't be that big. Edmund, 10 divided by essentially 12 cannot be 7. 0.796.
Yeah.
So at the instant when the balloon is 1 inch in radius, its radius is increasing about 0.8 of an inch per second. I want to do the problem again, please. I want to know what is dr dt when r is 5. My balloon's bigger. Bless you, Caleb. You're welcome. How does that problem look? 10 is equal to 4 pi times 5 squared dr dt, which means that dr dt is equal to 10 divided by 100 pi. Oh, I don't know if I trust you. 0.032 units, inches per second. Wait, so there at the very beginning, the radius is getting bigger at a rate about 0.8 of an inch per second. But as the balloon gets bigger, the rate at which the radius changes is now much slower. 0.03, 3/100ths of an inch per second. And guess what happened if I had you do this problem one more time? A really big balloon. What is dr dt when r is equal to 10? That's going to be 10 is equal to 4 pi times 10 squared dr dt, or dr dt is equal to 10 over 400 pi, which is approximately 0.008, less than 100th of an inch per second. And this is all based on the same rate of inflation, the same pumping up rate. The rates are related. They're not linear. They're not the same. They're related. Are we okay? Because what we're going to do is we're going to do 4 more examples. All of them are going to be different. All of them are going to start with this idea that we have an equation, but we want to look at the rates of change of the variables in that equation. We're going to change the V's into dVdt's. We're going to change the R's into dRdt's. The next one also has to do with the balloon. Are you ready? I am standing 500 feet from a hot air balloon launching. And the balloon is going up. There's my hot air balloon. I'm over here. I have something the book calls a, what do they call it? A rangefinder. And a rangefinder can tell me, oh, this is right at 500 feet, can tell me at what rate that angle is changing. So the balloon's going up, and I can see it going up, and as I point toward that bottom, as it goes up, I can find out the rate of change in the angle as I watch it go up. This angle here, theta, is increasing at a rate of 0.14 radians per second. My question to you, how fast is the balloon rising? You can imagine that if the angle went up very quickly, that the balloon would be going up very, very quickly. When that balloon, sorry, I got to add one more piece of this rate of change is when theta is equal to pi over 4. It's when I actually hit the pi over 4 measurement. I've right now given you enough information to figure out how quickly the balloon is rising. Let's go back to the earlier example. When we do the related rates questions, we start with an equation that we're going to take the derivative of. I need an equation that ties together variables that are related to each other. What are the things that are related to each other? Theta is changing, right? As the balloon goes up, my theta is changing. Theta is one of my variables. My other variable is right there. Let's call it height. Can you give me an equation that ties together theta and height? Tan? Tan. Tan. Because we have an opposite side, we have an adjacent side, and we have that angle. And this is a right triangle? Sure. Tan. Tell me more. Tan theta? H over 500. Everyone okay with that? Take fractions. How about 500 tan theta is equal to H? Are we good? Okay, step 1. getting an equation that ties the two variables that are both varying. Step 2, take the derivative of it. Typically with respect to time. What happens when we take the derivative with respect to time of 500 tan theta and the derivative with respect to time of h? Wait, is theta a function of time? As time passes, does theta change? Is h a function of time? As time passes, does h change? Yeah, I think we can imply that both of them are both of those statements are true, so that implicit differentiation comes back into play again. Okay, here we go. What is the derivative of 500 tan theta with respect to time? 500, because it's just a constant, secant squared theta, because it's an outside function, derivative, keep the inside the same, and then what's the derivative of the inside function theta? d theta dt. All right, what is the derivative of h with respect to t? dh dt. And if you had to explain this to your mother, what would you call dh dt?
Change of height.
Change of height with respect to time, or the speed is going up,
Right.
or velocity is going up. She's a stickler about science. Okay, the next step after the derivative step, by the way, plug and chug. Let's plug in everything we know. Do I know what theta is? Sure. Theta is pi over 4. Do I know what d theta dt is? Yep, that is 0.14 radians per second. And let's clean that up. What is 500 times secant squared pi over 4? I bet you I can do secant squared pi over 4. 1 root 2. Secant is going to be hypotenuse over adjacent. That's going to be root 2 squared. Root 2 squared is 2. That's going to be 1,000 times 0.14. I bet you that's going to be 140. It's going to be my dh dt. I only need one last thing, and I need my units. And this is going to be in feet per second. So, what's that? Is 140 feet per second fast?
No.
Yeah.
Yeah?
I would hope it would be.
Yes.
For
Is
a
it?
hot air balloon. Something
Even if you
airplane.
put it on the ground and you ran that fast, that would be.
That's per
Well,
second.
okay.
That's so
The,
fast.
the magnum at Cedar Point is 200 feet high.
So going that high in the answer, or basically.
So going the height of the magnum in about 1 second. That's pretty fast. All right.
Turbo powered balloon guy going there.
That's pretty fast.
Yeah, I was gonna say that's.
All right.
Actually, the brain. She's going to miles per hour.
I'm trying to hit a hole on it.
We're at the miles per hour. Yeah. Our stupid system.
You see that though?
All right. Next problem. Highway chase. All right. There's a police car. And the police car is heading south. And there's an intersection. And there's a speeder who's heading east. Speeder. All right. And let me tell you what we know about this situation. We don't know how fast the speeding car is going. But we do know how fast the police car is going. Police car is going 60 miles per hour. The other thing is that we have radar. And the radar gun is pointing at the speeding car, and it says that the change in velocity between our moving car and their moving car is 20 miles an hour. The change between P and S is 20 miles an hour. Our question is, how fast is the speeding car going? Well, let's start by assigning some variables to our situation. That distance I'm going to define as x. This distance down to the intersection, I'm going to define as y. And this distance z is fine. I typically use h for hypotenuse, but z is fine. Can you give me an equation that ties together x, y, and z? The Pythagorean theorem? X squared plus y squared equals z squared. Great. So far, so good. Now, what do I want to find out? I want to find out how fast the speeding car is going. Now, in calculus notation, what is it that I want to find out? The change in x with respect to t. How much is this distance here changing as time passes? So my question is, how can we find dx dt? Well, I know that from this equation, I can create a dx dt by taking the derivative of both sides with respect to t. So let's do that. Let's take the derivative of both sides of this equation with respect to t. So how does that derivative look? The derivative of x squared with respect to t, 2x dx dt. The derivative of y squared with respect to t, 2y dy dt. The derivative of z squared with respect to t, 2z to z dt. Now let's divide everything by 2. Because we can. Okay, we've got a relationship equation. We got the derivative of that relationship equation, which created things with derivatives. Plug and chug. What do I know? I know dy dt. That's the speed at which the police car is going. Tricky here, though. Watch out. Dy dt is negative 60. Why? Because the values of y as time goes on are getting smaller. So therefore, the derivative has to be negative. So dy dt is equal to negative 60. I think we also know dz dt. I think I read that the radar says that the relative distance between the two cars is 20. It's changing at 20 miles per hour. Okay? Now, one thing I forgot to tell you. Where these cars are when the radar hits. y is 8/10 of a mile above the intersection, and x, sorry, got it wrong. This is 0.6, and this is 0.8. 8/10. Yep. So now I have the ability to plug in a couple more numbers, and that is 8/10. I don't know what dx/dt is. Y is going to be 6/10, and z is let's see, 0.8 squared plus 0.6 squared is equal to z squared. 0.64 plus 0.36 is equal to z squared. 1 is equal to z squared. Z is equal to 1. Is that surprising? I hope it isn't. What's the most famous triangle pairing in many, many college entrance exams? 3, 4, 5. This is just a 3, 4, 5 triangle with a little bit of scale change. Alright, so there we go. There's a 1 for our z, and now we have enough information to solve for the velocity of the speeding car. Let's see if I can do this. 0.8 dx dt. This is going to be negative, probably like negative 36. Check my algebra, please. All right, let's add 36 to both sides, and I get 56 is equal to 0.8 times dx dt. Let's divide by 0.8, and dx dt is equal to 70, and units, miles per hour. Oh, and it's positive, because as that car's driving east, its x values are getting bigger.
You're on 8 mile, let's put it that way.
People drive 70 on 8 miles?
I'm sure it's happening.
I'm sure it's happening.
I would not be surprised.
No.
Maybe on 7 miles.
Doing speed
I drive on the Lodge every day,
Oh, that's insane.
and I drive the speed limit on the Lodge, and it is harrowing. All right, so there's another related rate problem. Are you ready for what's this going to be, our fourth?
Yeah.
Okay, do you notice how all of them are a little bit different? They're all story problems. They all have their own, they all relationship, derivative, plug and chug, solve. All right, let's take a look at, it's a classic. It is filling a conical tank. Now, if you want, it's a cone. This cone happens to be 10 feet tall, and its radius at the very top is 5 feet. Now, you can fill it with whatever you want. Ice cream? Ice cream's a little too viscous.
Melted ice cream.
Melted ice cream. There we go. As long as it doesn't have chunky stuff in it. Earlier today, we filled it with Red Pop.
Cookie dough. What maple syrup? I can get more maple syrup.
Maple syrup. Okay, maple syrup. Okay, so it's filled with maple syrup. Now, we are filling this tank,
That's the diameter.
the radius. The radius from here to here is 5 feet. Okay, now we're filling this tank at a rate of 9 cubic feet per minute. Our question is, how fast is the maple syrup rising when it is 6 feet deep? So we haven't filled it all the way to the top, but we're at the 6 foot mark. How fast is the level rising. You can imagine at the very beginning of the filling of the tank, it rises very quickly because there's very little volume in the very bottom of the cone. When you get up to the top, it rises very slowly. At what rate is it rising when it's 6 feet deep? Bet you there's a. How about we try to synthesize one of the pieces of information I just gave you? Ready? I'll say it one more time. Maple syrup is entering the tank at a rate of 9 cubic feet per minute.
What is the volume?
What's that? What is the volume of a cone? The volume of a cone is 1/3 pi r squared h. Okay? I would like in math notation, though, the idea that maple syrup is entering at 9 cubic feet per minute. I want it in math notation. dVdt? The rate at which volume is changing with respect to time? 9 cubic feet per. Okay. So, dV dt is equal to 9 cubic feet per minute. That's a lot of maple syrup.
It must be that spark maple syrup.
I get the Canadian stuff from Costco. It's delicious.
That's the fix.
It's like $15 a quart, but it's like liquid gold. No, Aunt Jemima was like cut with corn syrup. It's like, yeah. All right, so here we go. Now, I have a question for you. Is the height a function of time in this scenario? That over time, the height changes. Okay. Second question. Does the radius change as a function of time?
Yes, it
Oh, wait.
does.
Yeah.
Because down here, so radius is a function of time. Height is a function of time. They're both acting like these functions of time. All right. Now, question. Another question. I'm full of questions. When the syrup is 6 feet deep, what's the radius of the top of the cone? Not the top of the tank, but where the syrup line is. Less than 5 feet. Excellent.
Is yours gonna go?
I don't know if I'm in silent mode or not. I'm in silent mode.
Oh, you're gonna change it.
Yeah, change it quick. I think I'm gonna have to set mine a minute faster, so it's. This is disappointing. It's like an anticlimactic.
Comment till like the end of the minute.
I think so. Yeah. All right. So when this is 6 feet tall, how big is the radius here? There we go. Yes, it's cracking.
Could you use a proportion?
Could I use a proportion? I bow to Jordan Haynes, who's going back to revisit, what would that be, geometry. Geometry.
Okay, 5 over 10 equals 6 over X.
Okay. And indeed what we end up seeing is that there are similar triangles. Not congruent, they're similar. All right. And how about I write it this way? H is to R as 10 is to 5. Using the original maximum size. All the HR combinations, no matter what the height of the syrup, are going to follow that proportion. And using that, you could say I give you the height, tell me the radius. The radius is always going to be, oops, let me do 5h is equal to 10r, or 5/10 h is equal to r, or 1/2 h is equal to r. So if I told you we're at 6 feet of syrup, you're going to have a 3-foot wide syrup circle. Sorry, a 3-foot radius syrup circle. Now this makes something very interesting. This also means that every place I see r, I can replace it with 1/2 h. Before we take the derivative step, perhaps it would be wise to change that r into 1/2 h, so that when we take the derivative, we're only taking it with one variable. More than wise. Let me do a little bit of cleanup here. Volume is equal to 1/3 pi h squared over 4 times h, or volume is equal to pi over 12 h cubed. And I think at this point, I think we're ready to take the derivative with respect to h. No, not h. With respect to time. Respect to t. The derivative of volume with respect to time, dv dt. The derivative of that other side with respect to time, our constant, 3h squared, and don't forget the chain rule, dh dt. If we do a little bit of cleanup, we end up with pi over 4 h squared dh dt. And now we're ready for the plug and chug step. The plug and chug step. Do we know what dv dt is?
Yes,
9. Pi over 4 is a constant. Do we know what h is? We're interested in what's the rate of the height changing when h was 6. So 6 squared dh dt. 9 is equal to 36 pi over 4 dh dt. That 4 and that changes to a 9. Looks like dh dt is going to look like 9 divided by 9 pi. Oh, okay, 1 over pi. Units, please. Feet per minute. Why minute? Because that was the time frame that was given in the dv dt.
That's some great stuff, Sarah.
All right. And there's your classic conical take problem. Almost all the conical take problems, by the way, are going to have some sort of similar triangle thing that you're going to have to use that to get the relationship between r and h and get it down to one variable. All right. What's left? Nope. The ladder problem. Last problem. A 10-foot ladder is sitting against a wall.
I love doing that.
It's moving, the base is moving away from the wall at 2 feet per second. I'm going to call that dx dt is equal So the ladder is slowly slipping away from the wall at 2 feet per second. I said that not very slowly. Okay. Here I am. I'm standing underneath the ladder. To measure, I'm busy measuring how quickly the base is moving. I guess that's what it is. All right. My question is, how quickly is the top falling? How quickly is the top falling? Let's call this y. Let's get an equation that ties x and y together.
X squared plus y squared.
That's right. X squared plus y squared is equal to 10 squared. Let's take the derivative of that with respect to t. 2x dx dt. 2y dy dt is equal to 0. Because it's a constant. By the way, just one more hint on things that commonly make mistakes. Don't try to do the plug and chug. Don't try to do the, I'm going to plug values into my equation until after the derivative step. If you try to plug all the values in, you end up with constants on both sides of the equal signs, and you end up with a derivative that's just 0, and it's not very helpful. All right, let's divide by 2, get rid of those 2's. Now, wait, there isn't a constant rate at which the value of y is changing. When the ladder is nearly upright and it moves, the y value changes very little. But the further and further it goes, the faster and faster it falls. Okay? So how about we talk about finding the, let's try to find dy dt when x is equal to 3. All right? Now we're ready for plug and chug. X is 3. Dx dt is 2. Y is... Y needs to be found. 9 plus y squared is equal to 100. Y squared is equal to 91. Y is equal to the square root of 91. And dy dt, and there we go. We can solve dy dt from there. I take this over to the other side, and I get a negative 6. I divide both sides by the square root of 91, and I get negative 6 over the square root of 91. Wait, negative? Because the y values are getting smaller. Yeah, that makes sense. And that value, units here, is going to be
691.
feet per, I don't know, what did we say this was?
Feet per second.
This is feet per second. So this would also be feet per second. All right. Oh, that's joyful. That's a lot of fun stuff. All right. Huh? Homework. 1 through 35, odd. And then 36 through 41. Don't get frustrated. These are hard. Okay? And as we saw, as we did a couple of all these problems, they're going to rely on your prior knowledge from other math classes, like geometry. But do the best you can, and we'll go through a bunch of these problems tomorrow. All right. as soon as I stop the recording.